Okay, let's talk a little bit about the reaction quotient. N- Now, with the equilibrium constant, only concentrations that were supposed to go in there are equilibrium concentrations. That's not true of the reaction quotient. It has the symbol Q instead of K, and those values that you put in for concentration are not necessarily the equilibrium values, which is the main difference. So if we look at our generic equation, A reacting with B in equilibrium with C and D, you get a Q with the very same functional form as the K that we did in an earlier video. Now, some people might say, why do we need another equilibrium constant? We don't. And this really isn't an equilibrium constant. What we're using Q to determine is that if we're already at equilibrium. Now, as we compare the calculated value for Q with a known value of the equilibrium constant, and we know whether we're at equilibrium or not, and if so, which way is it going? So if Q is equal to K, then we know we're at equilibrium. So we know that the values we plugged in to the Q were actually equilibrium concentrations, and so we calculated the equilibrium constant, and no shifting of equilibrium would occur. If Q is bigger than K, that means we have too many products, because remember, products are on the top, so if I get more products, the value would be bigger, and so it's going to move to the left or towards the reactant side to a greater extent. If Q is less than K, then I don't have enough products. I got too many reactants. So reactants will go to form products, and so the reaction will still shift to the right to reach equilibrium. And so we can look at that as fractions. So if we look at this basic schematic, if Q equals 0, then we've only got reactants. And so the only way to shift is towards products, as we don't have any. So, and then if we're at K, it's not going to go either way. If Q was infinity, products only, meaning that the denominator was 0, so you would end up with some very large or undefined number. That means it's going to proceed to the left to try to get to K. Now, just that being said, you need to recognize that all products in a reactant situation, because if you try to divide something by 0, you're going to get a calculator error. And that's a good indication that as the denominator gets smaller, meaning fewer and fewer reactants, you actually approach infinity on the value of your number. And for those of you that are in calculus, you can do that. But if you take the limit as any fraction where the denominator approaches 0, the value of that function approaches infinity. And that's kind of the mathematics behind it. So if we look at some, for instances, let's say we've got this reaction H2 plus I2 reacting to form HI. So H2 plus I2 reacting to form HI, but it's in equilibrium. And we know that the Kc for that is 49 degrees at 450 degrees Celsius. Remembering equilibrium constant is a temperature dependent phenomena. So now let's say we got that in a 1 liter container. So 0.22 moles of iodine becomes 0.22 molar. And then we got 0.22 moles of H2, so 0.22 molar. If the volume's not 1, you need to divide through by whatever the volume actually is. And then we got 0.66 moles of HI, which would become 0.66 molar. Would the system be at equilibrium? If not, which way do we have to shift? So let's look at that on paper. And so I've transferred that over. So let's get a Q expression going. It's going to have the same functional form. So we're going to have concentration of HI squared divided by concentration of H2, concentration of I2. So we're going to end up with 0.66 molar squared divided by 0.22 molar squared. And so we need an actual value for that. So let's run that through our calculator. 0.66 squared divided by 0.22 squared. We get 9. So what can we say when we compare these two values? What we say is that Q is less than 49, right? Because 9 is less than 49. So, or we say it's less than the KC. So what does that mean? It means I need more products. So that means it's going to shift to the right, or it's going to shift towards products. And so that would predict the shifting in this particular case. Since Q is less than KC, we predict producing more products and consuming reactants. And that will happen until the KC and the Q are the same thing, at which point we'll say we're at equilibrium and the reaction would stop changing concentrations. All right, so let's look at this next problem. The equilibrium constant Kc is 3 for this particular reaction, and we have 0.8 moles of NO2, 1 mole of SO2, but it's a 2-liter container, so I have to divide that in half. So I'd have 0.500 molar SO2 and 0.400 molar NO2. And we want to know what the concentration of each substance is at the equilibrium, but I'm given the equilibrium constant in this case. So we need to do some comparison. So let's look at that on paper then. Which way is it going to shift? I have concentrations and reactants, but no products. So our Q would be concentration SO3, concentration of NO, concentration of SO2, concentration of NO2. But I don't have any products. So it's going to be 0 molar, 0 molar over 0.500 molar and 0.400 molar. So Q equals 0, which is certainly less than Kc, which equals 3, right? So, and that's a case where you could just maybe not do this calculation, because if I don't have any products, it has to shift that way. If I don't have any reactants, it has to shift that way. That being said, we know which way it shifts towards the formation of products. So let's get our ice table going. So we got concentration of SO2, concentration of NO2, concentration of SO3, concentration of NO. And then we got our ice table, initial, change, equilibrium, which is where the ice comes from. So plug in what we do know, 0.500, 0.400, bracket notation, so I don't need to write the m's for molar. And I started with none of that. I've got the equilibrium constant, but I don't know how much it changes. One way to get around that is to use a variable. So in this case, we're going to say that I gain x of that and that, because the stoichiometry is all 1 to 1, but I'm going to lose on the reactant side. And so I'd end up with 0.500 minus x, 0.400 minus x, x, and x. So now I can set up my KC. So KC is equal to what? It's equal to the same functional form there. So let's just copy it down. Now if we plug and check our variables, it'll be 0.500 minus x, 0.400 minus x. Those are my reactants. The products will go on top, and so it'll be over x squared. And that will be equal to our 3.00. Now I need to actually do some algebra. X squared is going to equal 3.00 times 0.500 minus x, 0.400 minus x. Just multiply both sides by those to get them in the numerator. Now I need to multiply everything out. So I'm going to FOIL out my thing, and then I'll save the 3, distribute it later. So working our math, 0.5 times 0.4 is 0.2. So we're going to say 0.200. And then what are we going to have? We're going to have a 0.5x, a 0.4x, both negative because the x's are negative. And so that'll add together to be a 0.900x, subtracting, and then plus x squared. Then I've got to distribute my 3. Is going to distribute in. So when we distribute that, we're going to get 0.600. 9 times 3 is 27. So that gives us 2.7x plus 3x squared. Now, get everything on the same side. I like to keep my x squared positive, so I'll move this over there, but then I'll just kind of flip it. So subtract that. So it'd be 2x squared minus 2.7x plus 0.600 equals 0. Now I've got a quadratic equation, just kind of moving everything over. Now, that may not easily factor, so we have to use our handy dandy friend, the quadratic equation. So our x is equal to what? Negative b plus or minus the square root of b squared minus 4ac divided by 2a. So where does that come from? So that this is your a, that's your b, including the negative sign, and that's your c. And you're just going to plug and chug at that point. So x is equal to negative b, so 2.7 plus or minus square root of b squared, so negative 2.7 squared minus 4 times a, which is 2, times c, which is 0.6, which I'll truncate some sig figs for space, divided by 2a, so 2 times 2. And so then we just need to run that forward. Let's do some simplifying. So x is equal to 2.7 plus or minus. Let's simplify what's in the radical. So we got 2.7 squared minus 4 times 2 times 0.6. Then so we get 2.49, and we'll square root that. I'll just go ahead and square root that in this step. And so we'll get 1.6, we'll say, divided by 4. And so x can be either the plus or the minus case. We'll have to use a little common sense to decide. And so 2.7 minus 1.6 divided by 4. So this is the minus case, is going to be 0.275. And so what about x in the plus case? 2.7 plus 1.6 divided by 4 is 1.08, we'll say. One of those answers makes sense, one of them doesn't. So we're going to pitch that one because concentrations have to be positive. So 0.5 minus x and 0.4 minus x have to be a positive number. So x is going to be equal to that, 0.275. So let's go back and reevaluate our equilibrium concentrations then. So the concentration of the SO3 equals the concentration of the NO, which equals x. And so x was equal to 0.275 molar. Concentration of the SO2 is equal to 0.5 minus x. And so we'll say 0.5 minus 0.273. We get 0.227 molar. Concentration of NO is 0.4 minus x. And so we'll say 0.4 minus 0.22 or 275 is 0.125 molar.